So now we need to look at a property of oscillations called damping. Now, most oscillations that you'll observe in your day-to-day lives will experience something called dissipative forces. That's anything that dissipates the energy in the system. And if the energy is getting less, then the amplitude will get less. So these dissipative forces can be anything from air resistance to friction, and what they will do is they will reduce the amplitude of your oscillation over time. And if a system is experiencing a dissipative force, we say that it is damped. Okay, we are damping down the oscillation. So there are three different types of damping that you need to be aware of. The first, light damping, is what would happen if you were to have a pendulum just set up normally in the lab, release it and watch over time. Air resistance will cause it to slowly lose energy, and as it loses energy, its amplitude will get less. And this will actually continue happening with each oscillation. And you end up getting a graph that looks like this. The time period remains constant. So the time for one full oscillation here, t, will be the same despite the fact that the system's experiencing damping. But what we end up getting is each successive oscillation dropping by the same interval. And so we get an envelope showing the dissipation and the reduction in amplitude. So each successive reduction is the same as the one before. So if it dropped by a half after one oscillation, it would drop to a quarter after the next oscillation, and then to an eighth, and so on. The next kind of damping that we need to look at is something called heavy damping. Now in heavy damping, you're going to get a drop in the amplitude, but this drop happens really gradually over a very long time. The key important thing about heavy damping is it never allows a complete oscillation to take place. You start at your maximum displacement or your amplitude, and gradually the whole thing dies down, but it never completes an oscillation. So it will return to its equilibrium position very, very slowly, but with no oscillating motion at all. The final one is critical damping. Now this is the kind of damping that you would want to use in something like a car, for instance. Now, if you're driving over a bump in the road in a car, your suspension is going to soften the blow of going over that bump. But you don't want light damping, because otherwise your car's going to be bouncing up and down forever. And you don't want heavy damping, because otherwise you'll bounce up and very slowly come back down, and then you'll bounce again, and this whole thing will have a cumulative effect. What you want is for your car to bounce up and very quickly get down to the equilibrium position, and that's what we get with critical damping. We don't get a full oscillation, it never drops below the equilibrium position. So we get the start of that cosine function, and we get the whole thing tailing off and hitting the equilibrium position, and this happens very quickly. Critical damping is the fastest of all three damping effects. It will hit the equilibrium position faster than any of the others. So those are three forms of damping. You need to be familiar with the pictures, and you need to be able to explain what those pictures are telling you.